Okay, today we're doing probability distributions. So, if you got a 50% chance of having a boy or a girl when you have a baby, okay? 50% chance of having a boy or girl so if this family has 3 kids, is it a 25% chance of 3 girls, 25% chance of 2 girls, 25% chance of 1 girl, 25% chance of 0 girls? Or does it follow this model, which 0.5 times 0.5 times 0.5, which is 0.125, or 12.5% of 3 girls? 2 girls and then a boy is 12.5%. A girl, boy, girl is 12.5%. A girl, boy, boy is 12.5%. A boy, girl, girl is 12.5%, and so on. Which one of these is an accurate reflection of how it works? B. Model B is the accurate model of how things work. So we're going to study Model B a little bit better. Each one of these is 12.5%. Now, when you write a sample space is what happens at each specific event. Up here in Model A, it was all just one event. Okay? Even when you have triplets, even when a lady has triplets, one baby comes out at once. Not all 3 come flying out at the same time instantly. Okay? One comes out at a time. There are 3 separate individual events. Okay? So, since they're separate events, we line them up in this, Oliver. We line them up using a tree diagram like this. Okay? This is called a tree diagram. So this is the first child, the second child, and the third child. Okay? So this, we would say GGG for girl, girl, girl. GGB for girl, girl, boy. GBG. And then GBB. And then BGG. And BGB. BBG. And BBB. So what's the percent probability of having all 3 girls? 12.5%. What's the probability of having at least 2 girls? Whoa. Don't just spit out 12.5%. At least 2 girls. There's 2 girls here. There's 2 girls here. There's 2 girls here. And there's 3 girls there. Because I said at least, not exactly. 50% chance of having at least 2 girls. So that would be how many of at least 2 boys? 50%, yeah, because it'd be kind of the same. What about exactly 2 girls? Exactly 2 girls. 37.5%. Okay? So, what's the probability that they have 3 girls? 12.5%. The probability that the first child was a boy and then they had 2 girls. Okay? Given that the first was a boy and then 2 girls. Well, that only happens once right here. So that's 12.5%. But then if they say they had exactly 2 girls, then that's 37.5%. Okay, next, probability distribution. Yes, vocab sheet. The probability distribution for a function assigns a probability to each outcome of a sample space for an experiment. So it's the probability of something happening. The probability distribution. Mm-hmm. Who never got one? How'd you never get one? How about you probably lost yours? Okay. So the probability distribution for an experiment is a function that assigns a probability to each outcome. So that's what we did just a little bit ago with the boys and girls. We assigned a probability 12.5% to each of the outcomes. Boy, girl, boy, 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 girl, boy, girl, and so on. Okay? So, Teo and Henry are running for president of student council. They each have 3 campaign buttons in a bag. Or in a box. You're going to pull out one campaign button. What's the probability it's Henry's? What's the probabilities it's Teo's? Okay? Now, if you pull out a Teo, that's half the buttons in there. If you pull out a Henry, that's half the buttons in there. Okay? So, what you do is you write, well, what's the probability of getting 0 Teos? 50%. What's the probability of getting 1 Teo? 50%. Okay, that's pretty simple. But then, now you plan to get a little more complicated. You're going to have 2 draws. The first draw is either Teo or Henry. Then you're going to put it back in and select again. So then you're going to have a second draw with either Teo or Henry. Okay? So, what's the probability of going Teo-Teo if each one of them is a 50% chance? So it's 1/2 times 1/2, which is 25%. What's the percent chance of going Teo Henry? 25%. What's the chance of getting Heo Henry? 25%. What's the chance of going Henry Henry? 25%. So what's the probability that you get 0 Teos? The probability of 0 Teos. 25%. Any more vocab sheets? Yep, there is. Today. At least 2 more today. Maybe 1 more today. I can't remember. What's the probability of getting exactly 1 Teo? What's the percent? There's exactly 1 Teo here and 1 Teo here. So it's 50%. What's the probability of 2 Teos? 25%. Okay? Now, by having a second draw, not everything's the same. If we only had 1 draw, these were the same. But by having 2 draws, that throws it off. So then, that's when our second vocab word comes up about uniform probability distribution. Okay? When they selected 1 button, the probability distribution was uniform. They were the same. Being the same is the same as saying being uniform. If they're not the same, then they're not uniform. So here's a good one. You're selecting balls or marbles from a bowl, okay? So you're going to select 1 marble and then put it back in the bowl. And then you select a second marble. What is the probability, okay? For each selection, you want to find the probability for selecting red marbles. So you're going to go the probability of red, the probability of 0 red, the probability of 1 red, the probability of getting 2 reds. Okay? So you're going to make out the sample space here. So if you draw, what are your two options? You either get a what or a what? Red or a green. The chance of getting a red is a 2 out of 5 chance. The chance of getting a green is a 3 out of 5 chance. On your second draw, what are your two options? Red or green. Okay? If you replace, if you put the marble back, you got a 2 out of 5 chance for red and a 3 out of 5 chance for green. 2 out of 5 chance for red, 3 out of 5 chance for green. Okay? So going red, red, what is your probability? 4 out of 25. Going red, then green is what out of 25? 6 out of 25. Going green, then red, 6 out of 25. And then going green, then green, 9 out of 25. What's 4 plus 6? 10. What's 10 plus 6? 16. What's 16 plus 9? So that's all 25 chances out of 25 chances are listed. Okay? This is called the sample space when you write them out. Okay? So what's the probability of getting 0 reds? 0 reds. 9 out of 25. What's the probability of getting 1 red? 12 out of 25. And what's the probability of getting 2 reds? 4 out of 25. Okay? Now, let's do it. Same thing, but we're not going to put the marble back in the bowl. Okay? So we want to find the probability of 0, probability of 1, the probability of 2 reds. Okay? But we're not putting them back in the bowl. So originally, there are how many reds and how many greens? 2 out of 5 chance of getting red, 3 out of 5 chance of getting green. Then, if I don't replace it and if I draw a red first, what's the probability of getting a red the second time as well? 1 out of 4. Because if you take a red out and you take a marble out, you take away each one of those. What's the probability of getting a green if you got a red first? 3 out of 4. What's the probability of getting a red if you got a green first? 2 out of 4. And how about green, green? 2 out of 4. Okay? So if you multiply across, you get a 2 out of 20 chance for going red, red. For going red, green is a 6 out of 20. Going green, red, 6 out of 20. Green, green, 6 out of 20. 2 plus 6 is 12, plus 6 is 8 is... Wait, 2 plus 6 is 8, plus 6 is 14, plus 6 is 20. I can't add. All right. So what's the probability of getting 0 reds? 6 out of 20, which is 3 out of 10, right? You got a 3 out of 10 chance of getting no reds if you draw and then you draw again. What's the probability of getting 1 red? 12 out of 20, which is 3 out of 5. And then what's the probability of getting 2 reds? 1 out of 10 chance. You got a 1 out of 10 chance. Okay? So this is probability distributions. Okay? We're going to skip over that one and we're going to look at binomial experiments. A binomial experiment, we're just going to write this much, and I know that's not the whole definition, but the definition's so long, I'm not going to make you write all that. A binomial experiment consists of a fixed number of trials, and it has 3 different features, but I'll just have you write down that much and call it good for writing it down, but we have to know what a binomial experiment is. So each trial has two outcomes. It's either you're going to be a success or not a success, which is a failure, but we don't want to talk about failure in math class. So successful or not successful, okay? Now, each trial is an independent event, and the probability for success should be the same for each time something happens to be a binomial experiment. Now, here we have go forward 2 spaces happening twice out of the 8 times, or a 1 out of 4 chance of getting go forward 2 spaces. So the spinner is spun 3 times. Assume the spinner is equally likely to stop at any sections. Success is landing on a spot marked go forward 2 spaces. So this is success. What is not success? If you got a 1 in 4 chance of being successful, what is not successful? 3 out of 4. Okay? So if you spin the spinner 3 times, what's the probability of at least being successful once? Probability of being successful once. Well, what this is a combination. So it'd be 3 combination 1, and then 1/4, you want to be successful at least once. So then the 3/4, well, you would be not successful how many times? Twice, because there's 3 trials. Okay. This is the binomial probability, okay, equation. Okay. So somebody on your calculator take 3 combination 1 times 1/4 times 9/16. 3 combination 1 times 1/4 times 9/16. What? 27 out of 64, which is what as a percent? So 42% of the time, you're going to be successful. 42% of the time, you're going to be successful. Okay? In a class of 23 students, 7 students are given a project. 2 students are selected from at random to give presentations. Success is a student has completed the project. Okay? So when the first student goes, the probability of them getting chosen to go is 7 out of 23. When the second student goes, it's 6 out of 22. Are those the same? No. The probabilities for each student are not the same because you're not going to have the same student go twice. So since the probabilities are not the same, that is not the binomial experiment because the probability has to be the same for each trial. So you'll have to know the difference between a binomial experiment and not a binomial experiment. Okay? But that's not as important as doing the binomial formula, which I just got done doing for that spinner wheel. And we'll do that here in a second. Okay? The binomial formula is a probability of being successful given on a certain number of trials is the number of trials and then the number that you want successful times the probability of being successful for the number of trials that you want times the number that you won't be successful out of the number of times you won't be successful. Okay? So, we're going to look at this one. Dana spins the spinner 4 times. The probability she gets an F. What is the probability that she gets an F exactly twice? She gets an F exactly twice. Okay? So, it's going to be 4 combination 2 because she spins it 4 times and successful for exactly 2 times is what we're looking for. Now, how many letters are there on there? 7 letters. So how many F's are on there? 1. So she's got a 1 out of 7 chance of being successful. And she wants to have that happen twice. So you take it to the second power. So then she has a 6 out of 7 chance of not being successful, and you take that to the second power because there's 2 times that she won't be successful. So 4 combination 2 is like 6. 1 over 7 squared is 1 over 49. 6 over 7 squared is 36 over 49. If you multiply all that out, that's like about what percent? 8%? 8.99, right?
No, it's 0.0899.
0.0899. So that rounds up to, you got about a 9% chance of spinning the spinner and getting F twice out of 4 spins. Okay? All right, tracksters. Have a good day down in Yankton today. Don't get struck by lightning. Don't get too wet in the rain if it rains on you. Okay? Run fast, turn left if you're running more than 100. Okay? Clear the hurdles if you're doing hurdles, and so on. Okay, I'm going to put out the assignment now. You guys can work your way through it.